Have you ever paused to wonder what truly makes incredibly complex systems, like the massive trains we see gliding down tracks every single day, remarkably safe? I mean, what's the hidden engineering, the mathematical precision, the technical artistry behind ensuring that something as monumental as a railway system almost never experiences a dangerous failure?
Yep.
We're talking about environments where, even the slightest miscalculation or component failure could lead to catastrophic consequences, yet they operate with this astounding, almost unthinking reliability.
It's an absolute fascinating frontier of engineering. It really is. And it underscores the profound importance of being able to quantify safety. This isn't just about, avoiding accidents. It's a rigorous, methodical approach. And perhaps
Totally.
paradoxically, by providing such a robust and measurable framework for risk reduction, it actually enables continuous innovation.
Right, because the baseline is secure.
Exactly. When you can precisely define, measure, and then reliably achieve specific levels of safety, you gain the confidence to design and build more complex, more efficient, and more technologically advanced systems.
Yeah.
It allows us to push the boundaries of what's possible, all while maintaining an incredibly high standard of reliability that, we as users often take for granted.
You've hit on something truly profound there, and today we're taking a deep dive into precisely how that quantification happens. Something called safety integrity levels, or SILs. We'll focus specifically on how they're applied in railway systems. We're going to unpack what SILs are, why they're absolutely crucial to modern engineering, and perhaps most intriguingly, how engineers manage to combine different components, often with varying individual safety ratings, mind you, to collectively achieve those incredibly stringent safety standards for an entire system.
That's our core mission for this deep dive, to really unravel SIL apportionment and allocation. This isn't merely about assigning a number to a system, no. Instead, it's about the incredibly intricate process of how safety requirements are meticulously distributed and then rigorously achieved across every single component and subsystem within a complex design. We'll explore how engineers don't just, hope for the best, they actively manage to minimize risk, addressing not only those unpredictable random events that can cause a piece of hardware to suddenly fail, but also those much more insidious, built-in design flaws or even subtle software bugs that could silently compromise safety from the very moment a system is conceived. It truly is a holistic approach, ensuring that every conceivable angle of risk is systematically evaluated and mitigated.
Okay, that's a fantastic roadmap for our discussion. Let's start with the absolute basics then. When we talk about a safety integrity level, or SIL, it's a term thrown around in safety-critical industries like rail, aerospace, nuclear power. But what does it truly signify? What is a SIL at its, fundamental level?
Right. At its core, a safety integrity level, or SIL, is a discrete number. Think of it not as a continuous scale where you can be like a 1.5 or a 2.7, but rather as distinct, defined steps. Much like gears in a car, maybe? Each of these numerical steps, typically SIL 1 up to SIL 4, represents an increasingly rigorous set of measures designed specifically to reduce risk to an acceptable level. Now, what's really important to understand is that these measures target two fundamentally different but equally critical types of failures.
Okay, two types.
Yeah. First, we have random failures. These are the unpredictable breakdowns of hardware components. Imagine a capacitor failing in a circuit due to, long-term wear and tear, or a tiny microfracture appearing in a metal part. These are events that occur spontaneously, often due to physical stresses, age, or manufacturing tolerances, and we can generally predict their rate using probability. For these random failures, a SIL defines a target hazard rate, or THR.
THR, got it.
Yes, this is a specific, measurable limit, the maximum rate of dangerous failures that a safety function is permitted to have. So it's a quantitative statistical target.
Okay, that makes sense for hardware breaking down randomly. What's the other type?
The other type is systematic failures, and these are not random at all. Think of them as fundamental design errors, subtle software bugs that lurk unseen until a specific condition is met, or even human errors that might occur during the design, manufacturing, or operational phases and get built into the system, so to speak. They're reproducible. If the specific conditions arise, the bug will manifest again, every time. You can't predict their rate with simple probabilities like you can with hardware wear out.
Right, because it's not about wear, it's about a flaw being present.
Exactly. Instead, you have to meticulously design them out through rigorous development processes, extensive verification, and thorough validation. This distinction is absolutely crucial, especially when we consider software. For software, we only consider systematic failures.
Only systematic. Why is that?
Well, because normal software, unlike hardware, doesn't degrade or randomly fail due to physical wear and tear. A bug in a piece of code will always be there, present under the same conditions, until it's fixed. It doesn't spontaneously appear or disappear. So for software, the focus is entirely on proving that the design is flawless and robust. It's all about the process, the verification, the testing.
That's a really clear distinction. So it's about making sure things don't randomly break down, and equally important, ensuring they're designed correctly, free from inherent flaws right from the start, covers both the unexpected and the built-in risks.
Yeah.
Okay, so if there are these different levels of risk reduction, how many SILs are there typically, and what do those numbers truly signify? Like, how much safer is SIL4 compared to SIL1?
Good question. You'll commonly encounter 4 different SILs: SIL 1, SIL 2, SIL 3, and SIL 4. These levels are meticulously defined within various international standards, like IEC 61508, which is a foundational standard for functional safety, and also EN 50129, which is specifically for railway applications. Each SIL corresponds to a progressively smaller, more stringent range for that tolerable hazard rate, the THR we just discussed.
Okay, so the numbers get smaller as the SIL gets higher.
Precisely. The acceptable rate of dangerous failures drops dramatically. To give you a feel for the magnitude, for SIL 1, we're looking for a dangerous failure rate that's less than 1 in 10,000 hours of operation. Less than 1 in 100,000 hours, but no less than 1 in a million hours. That's 10 UNR to 10 R per hour.
Okay, 1 in 100,000 hours. That still sounds relatively frequent for something running constantly.
It can be, depending on the system context. Now, when we move up to SIL 2, the requirements tighten significantly. Here we're talking about a dangerous failure rate of less than 1 in a million hours, down to 1 in 10 million hours. So 10 known at 10 million per hour.
A factor of 10 improvement.
At least, yes. Then for SIL 3, the stakes get even higher. The target is less than 1 in 10 million hours, down to 1 in 100 million hours. That's 10 into 10 air per hour.
Okay, another order of magnitude.
Right. And at the very pinnacle, SIL 4, the requirements are exceptionally stringent. We're aiming for a dangerous failure rate of less than 1 in 100 million hours, down to 1 in a billion hours. That's 1 to 10 LA per hour.
Wow, 1 dangerous failure per billion hours.
That's the target range, yes. So with each step up in SIL, you're demanding a tenfold decrease in the acceptable rate of dangerous failures. It's an almost exponential increase in required reliability. To put that in perspective, going from the bottom of SIL 1 to the bottom of SIL 4 is like reducing the chance of something going dangerously wrong from roughly 1 in 100,000 down to 1 in a billion for every hour it operates. It's truly pushing the boundaries of what's reliably achievable, demanding an almost unimaginable level of safety integrity.
That's a massive, almost mind-boggling difference in probabilities. 1 in 100,000 versus 1 in a billion per hour. We're truly talking about incredibly rigorous engineering. It sounds like an unimaginable level of safety is being targeted at those higher SILs. But this brings up a really important question. Can we truly compare a SIL 4 in one standard to a SIL 4 in another? Do they represent the same level of safety, even if the numbers might appear similar on paper? Is SIL 4 always SIL 4?
That's a critical question, and the nuanced answer is no, not universally, not always. Even if the numerical values for the tolerable hazard rates might appear similar or even identical on paper, SILs are not always directly comparable across all different functional safety standards. Let's dig into why.
Okay.
For instance, if we look at IEC 61508 and EN 50129, which are widely used, especially in Europe and often internationally, their THR values for each SIL are indeed numerically identical, as we just discussed them, so 10 or to 10 ranges and so on. However, if you then compare these to a standard like, say, DEFSTAN 0056, which is a UK defense standard, you'll see a significant difference in how they approach it. DEFSTAN 0076 often uses verbal equivalence for its hazard rates.
Verbal equivalence, like low, medium, high.
Sort of, but more specific. You might see terms like frequent, which is roughly equivalent to 10 O per hour, so 1 in 100. Then probable, around 10 O per hour, 1 in 10,000. Occasional, at 10 O per hour, 1 in a million. And remote, at about 10 O per hour, 1 in 100 million. While DEFSTAN 00056 does provide implicit target rates through these terms and other numeric values detailed elsewhere, the actual quantitative targets can differ quite a bit from IEC 61508 or EN 50129. The mapping isn't always perfect.
Okay, so the numbers themselves might not line up perfectly across standards.
Right. But the divergence goes even deeper than just the numbers. Even in cases where the THRs are numerically identical, such as between IEC 61508 and EN 50129, the measures required to combat systematic failures can vary.
Ah, the other part of SIL, the design rigor part.
Exactly. Think of it like this. You want to bake a cake to a very specific taste and texture profile. Two different master chefs might have recipes that aim for the same delicious outcome, but one chef uses a very specific blend of flours and a traditional kneading technique, while the other uses a special type of butter and a unique folding method. Both aim for the same end result, but the process, the ingredients, the techniques, the rigor of their systematic measures are different.
I see. So the how can be different even if the what looks the same numerically.
Precisely. This means that even if the probabilistic target, the THR, is the same, the practical steps, the design requirements, the verification processes, the validation activities required to claim that SIL can vary substantially between standards. This makes the SILs not truly identical in practice. Achieving SIL3 under EN 50129 might involve slightly different hoops to jump through than achieving SI3 under IEC 61508, even if the target failure rate is the same.
That's subtle but really important.
It is. Furthermore, some standards, like EN 50126, which deals with the overall railway ram's lifecycle reliability, availability, maintainability, safety. That standard doesn't even provide specific numeric target failure rates for SILs. It simply mandates the existence and application of SILs within the safety lifecycle process. And then there's EN 50128, which is dedicated specifically to software for railway control and protection systems. It focuses purely on systematic integrity for software and doesn't include numeric THRs at all because, as we discussed, software doesn't fail randomly in the same way hardware does.
Right. Software SIL is all about preventing those built-in systematic errors.
Correct. So what this really reveals is that functional safety isn't just about picking a number off a chart. It's about the entire rigorous approach, the specific design methodologies, the required evidence, and the context of the standard you are working within. For engineers, this means understanding not just the numerical targets, but the entire philosophy and detailed requirements behind the chosen standard, which brings us directly to a fascinating challenge.
Yeah, how do you actually build a system to meet these incredibly high safety levels? Especially if you're using individual components that, on their own, don't quite meet the overall system's required SIL. This seems like where the real ingenuity of safety engineering comes into play.
Absolutely. That's the perfect lead-in to the heart of our deep dive today, the art and science of combining SILs at what we call SIL apportionment and allocation. You've perfectly articulated the central engineering problem. How can individual components or subsystems, each perhaps rated at a lower safety integrity level, be effectively combined and integrated to create a larger system that ultimately meets a much higher, possibly even the highest required SIL?
Probably like using maybe a SIL 2 parts to build a SIL-A system. Is that the idea?
Exactly that kind of thing. This is the essence of SIL apportionment and allocation. The goal here is deeply practical. It allows engineers to leverage existing, often more affordable or readily available, certified components and integrate them in such a way that the overall system reliably achieves the desired safety standard. It's about designing a whole that is demonstrably safer than the sum of its individual parts. From a functional safety perspective, you're building safety through architecture.
Building safety through architecture. I like that. And you mentioned earlier that there isn't just one universal playbook for this. Different standards have different rules.
That's right. It's not a one-size-fits-all solution. Different standards indeed lay out different approaches and rules for these combinations. Let's look at a few common frameworks.
Okay. Where should we start?
Let's start with DEFSTAN 0056. The standard provides some relatively clear rules, especially when it talks about combining in parallel. Now, when components or functions are combined in parallel, it means that for the overall system to fail dangerously, both of the parallel components or functions must fail dangerously at the same time. Think of it like having two independent backup systems for the same critical function, like two separate brake circuits.
Okay, redundant paths.
Precisely. The rules in DEFSTAN 0056 for this are quite straightforward. If you combine two devices, each rated at SIL 3 in parallel, the resulting system can potentially achieve SIL 4. Similarly, two SIL 2 devices in parallel can yield an SI3 system, and two SIL 1 devices in parallel can achieve an SIL 2 system.
So basically, two of the same SIL in parallel gets you one step higher.
That's the general outcome suggested by these specific rules in DEFSTAN. It also says if you combine two devices with different S, say SLX and SELOY, In parallel, the resulting system will have an SIL that is the maximum of the two. So, for example, a SLA2 combined with a SLA3 in parallel would, under these rules, result in just a SLA3, not higher.
Okay, so you don't automatically get the benefit unless they're both at the lower level needed to step up.
According to that specific rule, yes. The key takeaway from DefStan 0056's approach here is that, in the most optimistic scenario, combining two devices in parallel typically increases the overall SIL by only one step. And critically, these general rules imply that you generally cannot build a system with a specific SI from components that don't have any SIL rating to begin with. You need some certified baseline.
Makes sense. You can't build safety from nothing. What about other standards?
Okay, let's briefly touch upon the Yellow Book. Now, this was a significant UK railway safety regulation, but it's largely obsolete now, superseded by European standards like the EN 504X series. But despite its age, it offers some interesting historical insights into combination rules. Its SIL definitions were aligned with EN 50129. The Yellow Book actually provided tables for combining SILs, often involving something it called a combinator element.
A combinator, what's that?
Well, it's not strictly defined in the material we reviewed in detail, but you can imagine a combinator as maybe a logical element. Perhaps a safety relay or a specific software module that acts as an interface or decision-making unit between lower-level functions. It ensures their outputs are correctly processed for safety. For instance, their tables might show that combining, say, a SIL2 function with SIL3 function and then routing them through a specific combinator rated appropriately could lead to an SIL4 system. This suggests a more complex structured interaction than just simple parallel addition. The integrity of that combinator itself becomes critical.
Interesting. So the way you combine them matters, not just the fact that they're in parallel.
Absolutely. Now, IEC 61508, the foundational standard, takes a different, arguably more granular and less straightforward approach than simple direct rules. It doesn't offer a neat single formula like DefStan sort of implies. Instead, its general rule for combining parallel elements involves selecting the channel within a combined subsystem that has already achieved the highest safety integrity level for its specific function. Then you conceptually add n safety integrity levels, where n represents the hardware fault tolerance, HFT, of that combination.
Hardware fault tolerance,
Yeah.
HFT. Okay, what does that mean exactly?
Hardware fault tolerance, HFT, essentially means the number of dangerous faults that the system can withstand and still successfully perform its required safety function. Think of it as how many individual dangerous failures the system can tolerate before it enters an unsafe state. If a system has an HFT of 1, it means it can tolerate one dangerous fault and still be safe. If it has an HFT of 0, it means it cannot tolerate any single dangerous fault without potentially failing dangerously. Simple redundancy often gives you HFT 1.
Okay, so higher HFT means more tolerance for faults. How does that relate to SIL?
Well, IEC 61508 goes further. Achieving a certain SIL also requires fulfilling specific criteria related to both HFT and something called the safe failure fraction.
SFF.
Safe failure fraction. As another acronym. What's this one?
Yes, lots of acronyms in safety. The safe failure fraction is a really crucial metric. It's essentially the ratio of a component's safe failures plus its detected dangerous failures, divided by the total sum of all its failures, safe plus dangerous, detected, and undetected. In simpler terms, it's about how much of a component's potential failure modes are either inherently safe, like failing to an off state, or are reliably detected as dangerous before they lead to an unsafe system state. It quantifies how safe a component's failure behavior is. High SFF is good.
Okay, so it's about whether failures are safe or detected versus undetected dangerous ones.
Exactly. And to apply these SFF criteria, IEC 61508 also distinguishes between Type A and Type B elements or systems. Type A elements are those whose failure modes are well-defined, their behavior under fault conditions can be completely determined, and there's ample, dependable failure data available. Think simple, predictable things like relays, resistors, maybe simple sensors. Type B elements are basically all other elements or systems. This category captures more complex, less predictable components, often those with complex software, microprocessors, ASICs, or novel designs, where failure modes aren't as exhaustively understood or predictable.
So simple and well understood versus complex and less predictable.
That's the gist. The standard then provides detailed tables, quite complex tables actually, that illustrate how combinations of SFF and HFT and whether you're dealing with Type A or Type B systems determine the maximum achievable SIL for a subsystem. While these tables aren't simple if this then that rules you can just memorize, an important pattern emerges when you study them.
Okay, what's the pattern?
If you increase the hardware fault tolerance, HFT, by just one, say, going from one channel to two identical channels, HFT0 to HFT1, while keeping the safe failure fraction, SFF, and the system type A or B constant, then the maximum achievable SIL generally increments by 1. This subtly implies that if you have two subsystems of the same SIL and similar SFF characteristics, combining them in parallel to get HFT1 could potentially increase the overall system's SIL by 1 step, aligning with the DefStan idea, but derived through a more complex framework involving SFF and component type.
Okay, so IEC 61508 gets there too, but through a more detailed analysis involving failure modes and predictability. What about other regulations, like in Germany?
Right, let's look at the German railway regulation, SURF 400, Sicherheitsrichtlinie Fahrzeug. This offers another set of principles, primarily for railway vehicles. Here, the rules for combining subsystems depend quite clearly on whether they are in series or parallel. When subsystems are connected in series, meaning they form an OR gate in a fault tree analysis, where if any one of them fails dangerously, the whole system fails dangerously. The resulting SIL of the entire system is determined by the smallest SIL of any individual subsystem in that series.
The classic chain is only as strong as its weakest link.
Exactly that principle. If you have a SIL3 component in series with a SIL2 component, the whole chain is only SIL2. Now, for parallel combinations, represented as an A gate in a fault tree where all parallel paths must fail dangerously for the system to fail dangerously, SURF 400 has several key rules. First, a system requiring an SIL greater than 0 must never be constructed solely from elements with an SIL of 0. Again, no building safety from non-safety parts. Second, the required SIL may often only be achieved by one SIL within an end gate unless specific exceptions apply.
Exceptions. What kind of exceptions?
These exceptions are crucial. One exception is where a single branch of the parallel combination is truly capable of completely taking over the entire safety function, providing full independent redundancy on its own. The other, and perhaps most significant exception, is when a thorough common cause failure analysis has been meticulously carried out.
Common cause failures. We haven't talked much about those yet.
We'll get deeper into them shortly, they're critical. But SURF 400 says if such an analysis is performed, then a suitable systematic method, like FMEA, failure mode and effects analysis, or HAZOP, hazard and operability study, must be rigorously used. This analysis needs to delve down to the lowest level of the hazard tree to definitively prove that common cause or common mode failures are absolutely excluded or sufficiently mitigated. SURF 400 even uses visual aids, like figures showing combinations in light gray for allowed, dark gray for forbidden, and white for conditionally allowed. The white areas are like a bright yellow warning sign. They signify that a deep, detailed analysis proving the complete independence of the subsystems is an absolute prerequisite before that combination can be considered safe.
So white means proceed with extreme caution and lots of analysis.
Pretty much. And generally, if we look across these SURF figures, neglecting a few highly specific edge cases, the pattern remains consistent with what we've seen elsewhere. Combining two subsystems with the same SIL in parallel would typically yield a system that is one step higher in SIL, provided that common cause failure independence is shown.
Okay, so different standards, different approaches, but a recurring theme seems to be this +1 SIL level for parallel identical subsystems, with caveats.
That's a good summary so far. Now, beyond these specific standard-based rules, we can also gain valuable insight by looking at a purely numerical approach based just on those tolerable hazard rates, THRs. While this approach doesn't initially account for systematic failures or those common cause issues, it provides a strong foundation for understanding the probabilistic side of redundancy. Let's make a few simplifying assumptions for this calculation.
Okay, lay them on me.
All right. First, assume no extra combinator element is needed, just two parallel subsystems. Second, there's an inspection interval T. If a dangerous failure occurs during this interval, it's detected at the inspection, and the subsystem is effectively made as good as new through repair or replacement. Third, our system is comprised of two identical subsystems connected in parallel. And finally, our goal is for the combined system to achieve an SIL that is one increment higher than its individual subsystems.
Okay, standard parallel setup with inspections.
Right. With these assumptions, the approximate rate of dangerous failure for the combined system can be calculated. Since both must fail for the system to fail dangerously, and failure in one is detected at interval T, the combined rate is approximately the failure rate of the first times the failure rate of the second times the inspection interval, so rate own T.
Lambda 1 times lambda 2 times T.
Okay.
Let's put some real numbers to this to see the power of this redundancy, numerically speaking. Let's use a common inspection interval, maybe 10,000 hours. That's roughly a bit over a year of continuous operation. Now, imagine you have two subsystems, each rated at SIS-1. The bottom end of SIL-1 is a THR of about 10 year per hour, one dangerous failure in 100,000 hours. If you want to achieve an overall system SIL-2, which requires a THR better than 10 ALA per hour, say aiming for 10 year, let's crunch the numbers. The combined rate would be 10 ALA per hour, 10,000 hours. That works out to 10 ALA is 10, which is 10 AL per hour.
Okay, wait. Earlier you said his STO was 10.6 to 10.7, so 10.6 just barely scrapes into SIL-2.
Ah, good catch. Let me recheck my source material calculation. Yes, apologies. The formula often used considers the probability of failure over the interval t, which for small rates, one is a proxylaxo, the probability of both failing is locus. The rate considers the repair. A simpler approximation for the rate of dual failure is indeed sometimes given as locus, but a more rigorous approach considering detection might be needed. Let's use the values cited in the underlying analysis for consistency, which showed strong numerical compliance. The core point derived numerically in the analysis was, if you take two SIL-1 subsystems, target e.g. 10 a row, the combined random failure rate calculation numerically meets the SIL-2 target, example 10 in a row. If you take two SIL-2, or example 10 off, they numerically meet SIL-4, and two SIL-3, example 10 RS, numerically meet SIL-4. So purely from a probabilistic standpoint of random hardware failures, this numerical calculation suggests that combining two identical subsystems can indeed achieve the target failure rate for one cycle level higher. It looks incredibly promising on paper.
That numerical approach certainly makes a strong case for redundancy on paper. It sounds incredibly effective. But here's where it gets really interesting, right? And where real-world engineering often throws a curveball. That calculation assumes perfect independence. What happens when you factor in those common cause failures you mentioned? Because in the complex, interconnected world of railway systems, things don't always fail in neat isolation.
Precisely. You've hit the nail on the head. That numerical computation, while illustrative and important for understanding the potential power of independent redundancy, it absolutely must be augmented, and in fact is often completely dominated by a rigorous common cause failure analysis. This is crucial because common cause failures, CCF, are simultaneous failures of multiple components or subsystems that would otherwise be considered independent, but they fail due to a single shared event or a shared cause or some underlying shared flaw.
Right, like the example you gave earlier, two brake systems failing because the shared hydraulic fluid leaked.
Exactly. Or think about two seemingly redundant electronic modules, but both get their power from the same potentially faulty power supply. Or they're located next to each other and susceptible to the same flood or fire. Or, maybe the most common one in modern systems, both run the exact same software. If there's a subtle bug in that software, it's a common cause that could make both modules fail under the same specific circumstances, despite being physically separate hardware. These aren't random independent breakdowns. They stem from a shared vulnerability. They bypass the redundancy.
Okay, so how do engineers account for this? You can't just ignore it if it dominates?
You absolutely can't. In safety engineering, to account for CCFs, we often use something called a beta factor. A beta factor is essentially an industry-derived estimate or a value determined through detailed analysis, representing the fraction of the total dangerous failure rate of a single component that is attributed to common cause failures affecting multiple similar components. So if we consider a perhaps pessimistic but often required scenario where a beta factor of 10%, beta equals 0.1 is used, that means 10% of all dangerous failures of a component type are expected to be due to causes that would also affect its redundant counterpart. And if that's the case, these common cause failures would actually dominate the dangerous failure rate for the combined redundant system.
Dominate. How so?
Let's use our example again. Imagine a single subsystem designed for SIL-HN, meaning its individual dangerous failure rate is roughly 10 HANR per hour. Where SIL-HN depends on the SIO bandwidth, let's simplify and say SIL for cell. If 10% of that rate is due to common cause, SIL-HN 0.1, then the contribution to the system failure rate from common cause alone is SLA. So the common cause failure rate for the pair would be approximately 0.1 10 HAR, which is 10 HAR over 10 HAR per hour. Let's try with specific SIs for clarity. Two SIL-2 subsystems, each aiming for SA change. The independent failure rate calculation gave us something very small, but if fell at 10%, the common cause failure rate contribution for the pair is VELO 0.1, 10 R will cause 10 HAR. Now compare that 10 R from common cause to the SL3 requirement of 10 R ups down to 10 R. The common cause failure rate itself is right at the edge of, or potentially exceeding, the SIL3 lower bound.
Wow. So the common cause failure alone basically sets the limit on how much safety you gain.
Exactly. The profound implication here is that without making further strong assumptions about how to drastically mitigate or completely exclude common cause failures, by using truly diverse components, different designs, different manufacturers, using totally separate power supplies, different physical locations, different software algorithms developed by different teams, without that kind of deep mitigation, simply combining two subsystems of the same SIL would, at best, only improve the overall SIL by one step. You cannot just multiply the probabilities for random independent failures and expect that to cover everything. Common cause failures introduce a hard floor, a fundamental limit on how much you can improve safety through simple redundancy alone. It's a critical reality check for safety engineers. You have to actively design against common causes.
That makes the design challenge much clearer. It's not just about adding more parts.
Not at all. So to synthesize these complex rules for combining safety integrity levels, it becomes abundantly clear. Beyond just meeting probabilistic target failure rates, THRs, the specific design requirements and the rigor of the development process, especially those aimed at preventing systematic failures and mitigating common cause failures, are absolutely paramount, particularly when you're trying to combine subsystems of a lower sessile to construct a system with a higher SI. Standards like DEFSTAN 0056 explicitly state that the appropriate design rules and techniques for each safety integrity level must be determined and applied before any implementation begins. And IEC 61508, along with EN 50129, provide extensive annexes detailing numerous different design methods, verification techniques, validation strategies, and documentation requirements needed for different SLs. CSI 4 consistently demands the most comprehensive and stringent set of these methods. It truly is not just about adding up numbers, it's about achieving a fundamentally different level of proven robustness and resilience against all types of failures.
So it really boils down to process, evidence, and managing those shared risks.
Precisely. The inherent challenge is that this extensive set of required methods, coupled with the subtle nuances between standards and the countless possible system architectures, well, it cannot be easily distilled into a single, simple, universal rule for combining subsystems that applies across all scenarios. It's just too complex. However, a powerful and very useful general rule of thumb does emerge from the patterns we've explored across different standards and the numerical analysis. It is often possible to achieve an SIL one step higher by combining two subsystems of the same SIL in parallel.
The +1 rule again.
Yes, it's a common and powerful design aspiration, but it comes with that critical, non-negotiable caveat we just discussed. Common cause failures must be meticulously accounted for and diligently mitigated in all scenarios. If you neglect these shared vulnerabilities, your perceived safety level based on simple calculations will be dangerously optimistic, far from reality. And just for completeness, let's not forget the rule for subsystems connected in series.
Right, the chain analogy.
Exactly. The resulting system's SIL will always be the minimum of the SILs of its individual subsystems. In a series connection, the weakest link truly determines the strength of the entire safety chain. No improvement there.
Okay, that's a lot of theory and rules. So all this about THRs, beta factors, HFT, SFF, different standards,
Yeah.
it can sound a bit abstract. Let's really make it concrete now with some real-world examples. This is where the genius of safety engineering shines through, right? What does all this mean for actual railway systems, and how do engineers apply these principles in practice to build the incredibly safe trains we rely on?
Absolutely. Let's walk through some practical scenarios that illustrate how these combination rules and the crucial considerations for systematic and common cause failures play out in actual system design. These are conceptual examples based on the principles.
Great, let's hear them.
Okay. Example 1. Let's imagine a system consisting of two independent hardware subsystems with no software involved. Pure hardware redundancy. Picture this. Each of these two hardware subsystems is continuously monitoring the other, cross-checking. If one detects any discrepancy or difference in operation from the other, indicating a potential fault, the system is designed to immediately and safely shut down. Fail-safe. Now, if both of these truly independent hardware subsystems are individually rated at SL3, they could potentially be combined in parallel to create a system that achieves SL4.
Justly, the +1 rule in action.
Yes. And this is often considered feasible because the stringent design rules and systematic measures already required for SL3 are generally quite similar to those for SL4 in many standards. The leap isn't a massive shift in fundamental design approach, just more rigor. Similarly, if you start with two SL1 subsystems, they could likely combine to form an SL2 system. However, if you have two SL2 subsystems and your ambition is to achieve an SL3 system, this usually requires a much deeper, more rigorous investigation.
Why is the SL2 to SIL3 jump harder?
Because the step up in required systematic measures and design rigor between cell L2 and cell L3 is often significantly larger than the step between LL3 and cell 4 or cell L1 and cell L2. Achieving cell L3 often demands fundamentally different, more demanding design techniques, verification methods, and independence arguments compared to cell L2. It's less straightforward than the other steps. It often marks a major shift in required engineering effort.
Okay, so the gap isn't uniform between levels. Got it. Example 2.
Example 2. Very similar to the first, but with a critical difference. Both hardware subsystems use the exact same software. Imagine a single identical software package controlling two parallel hardware paths.
Ah, the common cause software problem we talked about.
Precisely. The challenge here is immediate. Any systematic bug or flaw in that single version of software would inherently affect both hardware subsystems simultaneously, potentially. From a functional safety perspective, this identical software effectively acts in series with the two parallel hardware components, creating a potential single point of failure for systematic issues. The key rule here, driven by this commonality, is that the software's SIL rating must be at least as good as, or possibly even better than, the overall system's required SIL. The software becomes the limiting factor for systematic integrity.
So the software has to match the target system SIL.
Generally, yes. So, if your entire system needs to achieve SIL4, the single version of software running it must also be developed and verified to SIL4 standards. You could construct an SIL2 system from two parallel SI1 hardware systems, but only if that common software itself is rated at least SIL2. If the system needs to be SIL3, the software must also be SIL3. And just as in our first example, if your individual hardware systems are SIL2 and you're aiming for an SIL3 overall system, even with SI3 software, you still need those additional considerations due to the hardware design rules jump, plus you have the common software vulnerability. The identical software creates a critical common cause failure point that fundamentally limits how much you can gain from hardware redundancy alone against systematic faults. It's like having two excellent cars, but both rely on the same potentially flawed navigation software.
Okay, that makes perfect sense. So diversity becomes key.
Exactly. Which leads us to example 3. Hardware with diverse software. Again, similar setup. Two hardware subsystems, but now they are running different diverse types of software. This diversity is absolutely paramount. Its primary aim is to mitigate the risk of common cause failures arising from systematic software bugs. If the software is truly diverse, meaning it's maybe developed by different teams, using different programming languages, different algorithms, perhaps running on different microprocessors or operating systems using different tools, then a systematic bug in one software version is far, far less likely to be present in the other.
Reducing the chance that the same flaw exists in both.
Correct. This significantly enhances the safety architecture against software faults. Because this software diversity helps manage those systematic software failures, the SIL apportionment considerations become much more akin to our first example, pure hardware, at least regarding the software aspect. So you could, again, potentially construct an SIL4 system from two SIL3 subsystems, where each subsystem now consists of SIL3 hardware and its own SIL3 diverse software component. Similarly, two SIL1 subsystems, each with its own SIL1 diverse software, could combine for an SIL2 system. And still, aiming for an SIL3 system from two SIL2 subsystems, each with SIL2 hardware and SIL2 diverse software, still requires those additional detailed considerations about the increased rigor in design and verification processes required for SIL3, particularly for the hardware aspects. But the software common cause risk is much lower.
Diversity helps a lot, but doesn't magically solve the hardware rigor jump between SIL 2 and 3.
Precisely. Okay, example 4. A system with only one hardware channel, but it utilizes redundant software. This redundancy typically comes from two distinct software versions, or perhaps through specific redundant programming techniques within a single program. But the critical point is that software diversity must be ensured. Just running two copies of the same code isn't enough.
The single hardware, but diverse software checks. How does that work for SIL?
If the overall system needs to achieve SI4, then the single hardware channel itself must be capable of supporting SI4 requirements, in terms of failure rates, diagnostics, etc. Furthermore, both the diverse software versions running on it must typically be rated at least according to SIL3. And it's not just about the ratings, it's also absolutely critical to rigorously prove that any hardware failure that might occur is reliably detected by both diverse software versions, and that the system has robust mechanisms to always transition into a predetermined safe state if such a hardware failure occurs. The software needs to reliably detect hardware faults.
So the software protects against hardware failure too? What about lower SILs?
If the system's requirement is SL2, Then the hardware would need to be SIL 2, and you'd need two independent, diverse software versions, perhaps rated at SI1 each, again, provided they can detect the relevant hardware failures. However, just like our earlier examples, if you're aiming for an SIL 3 system with SIL 3 hardware, trying to use two diverse SIL 2 software versions requires a highly detailed study. The question of whether two software versions running on the same hardware can truly be considered fully independent, especially concerning common cause failures originating from the hardware platform itself, like a faulty CPU clock affecting both, is, as the analysis states, not trivial.
Right. The shared hardware is still a potential common cause, even if the software logic is different.
Exactly. Despite the diversity in software logic, the common hardware platform introduces potential common cause failure modes that demand extremely careful analysis and robust mitigation strategies. It's a significant engineering challenge to prove sufficient independence when software shares the underlying hardware.
Okay, one more example.
Fifth and final one. Imagine an electronic subsystem, which includes both its own hardware and software, operating in parallel with a completely separate hardware bypass system. This bypass system acts as an independent, often simpler, purely hardware-based safety layer. Think of it like a mechanical overspeed trip alongside an electronic control system.
Okay, a complex electronic path and a simple, robust backup path.
Exactly. This setup offers truly interesting possibilities for SI allocation. For instance, scenario 1, if the hardware bypass system alone is capable of meeting the system's overall required SIL, meaning it's robust enough to handle the safety function entirely on its own if the complex electronic subsystem fails, then the electronic subsystem, consisting of hardware 1 and software 1, might not strictly need to have any specific SIL assigned to it for the overall system safety goal. Its failure wouldn't compromise the overall safety if the bypass is robust enough on its own. The bypass provides the guaranteed safety level.
So the electronic part could be less rigorously developed if the backup is strong enough.
Potentially for that specific safety function, yes. The bypass acts as the ultimate failsafe, meeting the SIL requirement independently. Alternatively, scenario 2. If both sides are necessary to achieve the desired safety level through their combined action, then the same logic we saw in example 1, pure hardware, or example 3, diverse software, can often be applied. An SIL4 system could conceivably be constructed by combining two SIL3 subsystems. Here, the electronic subsystem, hardware 1 plus software 1, acts as one SIL3 subsystem, and the independent hardware bypass acts as the other SIL3 subsystem. In this configuration, it's generally required that the software within the electronic subsystem, software 1, must have a SI rating that is at least as good as, or even better than, its accompanying hardware 1. This ensures that the software doesn't become the weak link in that particular electronic channel.
So you treat the electronic part and the bypass part as two parallel channels.
Essentially, yes, if both are needed to contribute to the SIL target. These examples really highlight the meticulous, varied, and frankly ingenious approaches engineers take to achieve these incredible safety levels. They go far beyond simple redundancy to address complex failure modes, systematic issues, and common cause vulnerabilities.
These examples truly illustrate that engineers in functional safety aren't just making educated guesses, they are following exceptionally specific rules, conducting rigorous analyses, and making incredibly careful, deliberate design choices to achieve these remarkable safety levels. It's a testament to the sheer depth of rigor and detail involved. Every potential failure seems considered, quantified, and mitigated.
You've encapsulated it perfectly. To bring all these threads together, what we've clearly seen today is that while there is no single, simple, universal rule for SIL apportionment that applies uniformly across all countries, industries, and specific situations, largely due to the varying standards, definitions, and complex interdependencies we discussed, a very common and tremendously useful rule of thumb for parallel combinations is to aim for a SIL that is one step higher by combining two subsystems of the same SIL.
The +1 guideline.
Yes, it's a powerful design principle, a common target, but it is fundamentally dependent on that one absolutely crucial factor, the diligent accounting for and robust mitigation of common cause failures in all scenarios. Without adequately addressing these shared vulnerabilities, simple redundancy calculations can be dangerously deceptive.
That seems to be the biggest takeaway. Watch out for common cause.
It's certainly one of the most critical. For truly complex system architectures, general rules can only guide you so far anyway. These systems often require highly detailed, specific safety studies that delve deeply into the unique characteristics, potential failure modes, and interaction points of that particular configuration. The ultimate unwavering goal remains constant: to ensure that the overall system's target failure rate is never exceeded under any foreseeable circumstance. That's the bottom line. And just to reiterate for completeness, the rule for series connections is much simpler and stricter. When subsystems are connected in series, the resulting system's SIL is always limited by and equal to the minimum of the SILs of its individual subsystems. The weakest link sets the bar.
So the next time you see a train effortlessly gliding through a station, or perhaps any complex automated system, maybe a self-driving car navigating busy streets, or a modern power grid managing electricity flow, or even critical medical devices in a hospital, consider the unseen, meticulously engineered layers of safety built into its very design. It's not just about constructing robust individual components. It's about profoundly understanding how those components interact, how they might fail individually and together, and the ingenious ways engineers combine them to achieve astonishing levels of integrity that protect us every single day. This depth of engineering thought goes far beyond simple redundancy and delves into a fascinating world of quantified risk, systematic design rigor, and continuous vigilance. What other everyday systems, perhaps ones you interact with constantly without a second thought, do you think quietly benefit from these kinds of safety integrity level considerations? Something to ponder. We hope this deep dive has given you a newfound appreciation for the silent, often invisible guardians of safety in our modern, complex, interconnected world.